Hey everybody, and welcome back to Algebra 2 Online. So this is going to be another review video just covering a bunch of different things from this course. All really important problems to make sure you know for the upcoming final. So first one are just two log equations, or not log equations, two trig equations. Anytime you see these trig equations, you should try to think about how to simplify things. It's going to make it all the easier to figure everything out here. So, this one, you have, I might actually erase some of this here in a second. You got a cotangent on the bottom, so that's like, instead of sine over cosine, which is tangent, right? It's cosine over sine. And then we've got a cosine. And then we've got a sine over cosine, right? Because that's what tangent is. So this part and this part would actually just cancel off, right? Because the cosine and the cosine, the sine and the sine. And so this whole big thing right here will actually just simplify fully to 1 over cosine, equals 2, I should say, or cosine of x equals a half, right? If you just flip, if you do 1 over each side, it should still be equal. So cosine of x equals a half. Now, this is the point where you can kind of just think of the unit circle. And we got the all students take calc thing. And so we can't be in this quadrant or this quadrant, right? Because cosine's only positive in these two. And then I would just use the finger trick thing. I want for cosine, square root of fingers above over 2. And the finger that kind of relates to that is like a pointer finger. So it's like a 60 or like a pi over 2. Pi over, not 2, sorry. Pi over 3. Let's do it. Let's just do it in degrees. So we'll have x equals 60. And that would be, the one in this quadrant. Or we could have one down here, and to get to there, right, we'd have to go around 300. So the other one is 300. And that is the only two that we'll have because we wanted the answers in the first lap of the circle, basically. For this one, it says find the exact solutions to sine 2x over 2 cosecant squared x equals 0 on one lap again. And so here I'm saying, this one seems pretty scary looking. You got double angle in there and stuff. But if you just think about what it means for a fraction to equal 0, it's really not too bad. Like if this fraction equals 0, that's only going to happen if the top of the fraction equals 0, right? So sine 2x needs to equal 0. And to do those, right, we could use a trig identity, or I have in that that last trig video I showed how you can kind of use substitution here to do it too. So maybe I'll show both ways. So let's do the trig identity way. So sine 2x, we know, and I will give you these trig identities, but it equals 2 sine x cos x. So one way to do this is to just write this as 2 sine x cos x equals 0. You can divide out by the 2. And so you basically have two problems now, right? Sine of x needs to equal 0, or cosine of x needs to equal 0. If you're thinking unit circle, right? And you're thinking about where things equal 0, for sine you're thinking y values, right? So that would be on here and here. So, there's going to be two y values that equal 0 in the circle. And then cosine of x equals 0 is the x value needs to equal 0 in the circle. So you get basically a solution at every, point on the axis like that. So you're basically getting a solution at pi over 2, also 0. So 0, pi over 2, 3 pi over 2. Nope, I skipped one, sorry. Pi. 3 pi over 2, or, 2 pi, but 2 pi is 0, and it's also we don't include the 2 pi. It's open interval there, so we're not going to actually include that. So this is one way to do it, but I want to kind of show you another way. So we also had this kind of idea where we can do the substitutions thing, where we're going to let 2x basically be some sort of placeholder like theta, and then we're going to solve sine of theta equals 0, right? So sine of theta equals 0 happens, right, if you think of the circle, right? It can happen at 0, or it can happen at pi. Again, it's just where y value equals 0. So theta equals 0, or theta equals pi. But then you got to unsubstitute, right? So theta is 2x, so 2x equals 0, or 2x equals pi. And so if you just divide by 2 on that, you'll get x equals 0, and then here you're going to get x equals pi over 2. But there's one other thing we need to actually consider here before we talk about our final answer. So we really should have like plus like 2 pi n plus 2 pi n. And before like you divide by 2 and just say that's all you get, right? You could also divide by 2 here and divide by 2 here, right? And so, because like we're noticing we're getting like 2 answers versus 4. So there's something, other answers that could pop out of this. And so, if you divide by 2, it really would be like 0 divided by 2 is still 0, but then 2 pi n divided by 2 would be plus pi n. And so that's, how we get 0 and pi. And then in this one, pi divided by 2 is pi divided by 2, but then 2 pi n divided by 2 is pi n. And so you basically would get that one and that one, because if you add more than one multiple of pi, you're going to go outside of the full lap, which is all we wanted. So you still get all 4 answers, but you have to be a little more careful with that. But there's even more to it, because this is a very tricky little problem, but we were just working with the top, and if you were solving sine 2x equals 0 in the first lap, you would get these 4 answers, or you can get the 4 out of here too. But we really actually did have this too, and that is going to give us some sort of domain issue. You need to consider that. And so, that is going to be, this means that we're going to be undefined whenever sine of x equals 0, because 1 over sine is cosecant, or 1 over sine squared is cosecant squared there. But if you get a 0, right, it's going to be undefined. So anytime you have rational functions in math, you have to think about domain. You have to think about, am I going to divide by 0? So you take your answers, whether you write them like this or write them like this, and you need to think about where they're undefined. So sine of 0 is 0, so we got to throw that out. Sine of pi over 2, not 0, so it's going to be fine. Sine of pi, though, is 0, so that's not good. And sine of 3 pi over 2 is fine. So final answers that you would have in this problem would be pi over 2 and 3 pi over 2. This would entirely get thrown out because of domain. So you could also write it as x equals pi over 2 plus pi n, where n equals 0 and 1. If it equals 0, you get the pi over 2. If n equals 1, you get the 3 pi over 2. So don't care how you write it. That's probably the more obvious way to write it. But 2 ways to do the same problem. And don't forget about domain. Very tricky little problem there. All right. Another really important thing in this course is just solving log equations and inequalities. Another type of problem where domain plays a really big role, so we have to think about that. Might as well just do it right now. So for the domain part, we need 2x minus 1 to be greater than 0, or x to be greater than a half, right? We also need this 4x to be greater than 0, or x to be greater than 0. So, we just need the inside of logs to always be greater than 0. So if you compare these two, right, you need the more restrictive thing, right? And if you're bigger than a half, you're already bigger than 0. So we're not actually going to need that one. Later on, this may become an important part of the problem somehow, though. So jumping into the solving of it, I'd probably move this log over. So I'd have log base 3, 2x minus 1, plus log base 3, 4x is greater than 2. You've got a sum of logs with the same base, so you can multiply the insides. Log base 3 of 2x minus 1 times 4x. All that's greater than 2. And then you want to just cancel the log. So you're going to do, 3 to both sides, like 3 to this log will cancel it. Then you can go ahead and just have 2x minus 1 times 4x is greater than 8, right? And now we just got a quadratic inequality. So solving quadratic inequalities should be kind of second nature. You multiply this out a little bit. We're going to have minus 4x there. Let's actually divide everything by 4, right? Nope, I just realized I'm looking at this, I'm like 3 squared, 2 cubed is 8. I was like dyslexic there for a second. 3 squared is definitely 9, so let's do 9 into 9. And now, sadly, we can't go ahead and divide everything. We just got to deal with those numbers. So I would probably just jump right to the quadratic formula. If you do out the roots, you'll get x is 4 plus or minus square root 16 minus 4 times 8 times negative 9 all over 16, which simplifies to 4 plus or minus root 304 over 16. And so thinking about the picture, right? I don't know where these roots are exactly, but I know that 4 minus square root of 304 is below on the number line 4 plus square root of 304. And then we've got, this kind of thing where the quadratic is like opening up. And we want specifically a greater than 0 situation. So this is my 0. I want to go greater than it. So I want to talk about that part and that part. So it's some sort of or. So x is less than, let's actually give myself a little room. X is less than the small root. Or x is bigger than the big root. And now we just got to go back to the domain that we talked about. So we need to make sure that these numbers are both bigger, like everything in here and everything in here, if it's going to be part of my answer, it better be bigger than a half, right? Square root of 16 is 4. And so square root of 304 is much bigger than 4. That's the idea I want you to see. So this number, right, has to be negative. And since a negative number is not bigger than a positive number, we will have to literally chuck that answer out. So no more or at all. This is a problem that reduces to just that. And 4 plus the square root of 304 is definitely divided by 16 bigger than a half. So you can check it if you want, but it is bigger than a half. So everything in there will solve the inequality. These are really good problems to know. Definitely lots of good stuff I'm testing here. I can test quadratic inequalities. I can test domain, just basic equation solving stuff. well, I guess inequality stuff, quadratic formula. I mean, there's so much stuff in this problem. Definitely the kind of thing you want to make sure you understand how to do. All right. This problem just asks us to sketch a rotational angle of negative 4 pi over 3, then find the sine, cosine, tangent, cotangent, secant, and cosecant of this angle. So to do that, I'm just going to start off and draw my angle. So, the way I think about this really is it's negative, so it's going clockwise. A little weird, but basically it doesn't follow the order of the quadrants. This is 1, 2, 3, 4, right? So we're going backwards, so negative. And I'm basically just going to tick off pi over 3s, right? Pi over 3 is like 60 degrees, right? So 1 pi over 3 is kind of here, 2 might be here, 3 would be exactly here, right? Because 3 pi over 3 is pi. And so 4, you're going to get an angle that kind of takes you around, to right there. That's negative 4 pi over 3. Ends in quadrant 2. And we will need this anyways. I might as well put this all students take calc thing. The only ones that are going to be positive, right, are going to be sine in that quadrant. So all the other ones in that quadrant will be negative. So the only answer that's going to end up being positive is anything involving sine, which is, of course, sine, and over here, cosecant too. So then let's just kind of write this down. So sine of negative 4 pi over 3. Basically, it's just you're doing a finger trick thing with a reference angle of 60. So 60 is your pointer finger. You do square root of the fingers below over 2. So square root of 3 over 2. And that's it, because it's positive. You might as well do cosecant. Not cosine, sorry. Do cosecant, because cosecant of negative 4 pi over 3 is just 1 over this, right? So it's just going to equal 2 over root 3. For cosine, negative 4 pi over 3. Still looking at your pointer finger, just go up this time. So square root of 1 over 2. Square root of 1 is 1. But it is negative because sine is positive in that quadrant. Then secant, right, of negative 4 pi over 3 would just be the reciprocal of negative 1/2, or just negative 2. Last but not least, we'll do tangent, negative 4 pi over 3. For this one, you can really just do sine root 3 over 2 over cosine, right? And so if you do that out, you're just going to get, sorry, hold on. The 2's would cancel, right? And you'll just get negative root 3. And so you could do cotangent really quickly from there, because you could just flip negative root 3 upside down, basically, and you just get 1 over negative root 3. No calculator involved here at all, just kind of finger trick stuff. Yeah, that's another just really, really, really important kind of thing to know. Working with the unit circle is like an incredibly important part of this course. Another really important thing is just simplifying log things, just like I want you to be able to do, these in your head without a calculator. If I give you this big, messy looking, scary thing, I want you to be able to do this in your head. Maybe not all in your head, but be able to simplify it, definitely. So, some of the stuff I'm kind of seeing, it is actually a pretty nice one. You've got log base pi of pi, right? So that's set up to cancel. And so one thing on the top here is you're basically just going to have pi, and then the whole thing was squared. So you'll have a pi squared on top so far. Right here, we're doing x times x to the 0. Well, x to the 0 is 1, right? Anything to the 0 is 1. So that whole little bit right there could just simplify to an x. This part in here this is a base 10 log, right? When I don't write the bases, that's 10. And this is 10 to the negative 1. So this part, we have this whole thing multiplied. This thing is, log base 10 of 10 to the negative 1. So that's really just negative 1. This is log base 10 of 100, but 100 is 10 squared. So that part is just a 2, right? So now you've got pi squared over x times 2 minus 1 is 1. So this whole messy looking thing just simplifies to pi squared over x. Definitely need to know how to simplify logs. I don't want you to go into your calculator to know that like log of 100 is 2. 10 squared is 100, which is why log of 100 is 2. Definitely important part to understand is how to simplify logs. We need you to be able to do that kind of stuff nice and efficiently. All right, just one more problem I'm going to do in this video. I just want to graph 2 cosecant negative 2x minus 1. And to do this, basically we're going to graph 2 sine, I don't want that parentheses, sorry. I want 2 sine negative 2x minus 1, right? And the way to graph any sine or cosine, just start by doing the whole period thing, 2 pi over b. B is 2, and so 2 pi over 2 is pi. And so we have a full, period in 0 to pi. So any increments of that, you're going to see a full cycle of this graph. So to graph this, I'd probably start by shifting it down 1, get that midline on here so that everything's going to be kind of symmetric with that. Then you can see that we go, the vertical stretch factor is 2. So we're going to go 1, 2 off of that. And we're going to go 1, 2 down from that midline. So then, maybe instead of dealing with this negative is a horizontal flip. So maybe what I'll do kind of as a first step is do 2 sine x minus 1. 2 sine x minus 1, you would start here, sine of 0, 0, here it's shifted down, but then at, our period's pi, so at pi over 4, right, little halfway mark here, you're going to go up to its highest point, and so it's got a vertical stretch of 2, so you go up 1, 2 again, and so we get that point, and then we'll come back down, over here, and then at 3 pi over 2, you'll be down 2 off the midline, so that's 1, 2, so you'll be about here, and so, let's see, that is halfway there, and then, you just go back to the midline at the end of the one full cycle, which in this case takes pi radians to do. So that graph is basically what 2 sine x minus 1 looks like, but we have a negative in there. We have a horizontal, flip, and so this point would move over here, right about there. This point would move right over there. This point won't move, right? I guess I should have said that first. And then this point would move over. You're going to be right there. And then this point also moves over, right there. So, I don't really need these points now. And that right there is roughly what 2 sine minus 2x minus 1 is. But we are graphing cosecant, right? So we want to do the thing where now to get cosecant from that, we just take, anywhere there would have been like a 0 or anything on the midline, right? We are going to have asymptotes. And then the reciprocal of these peaks and valleys would stay the same. And then basically you just draw in that kind of general, like, weird parabola kind of looking thing. And it would just continue, like that. The next one would be up here, and then down here, and then so on. You'd have one here, and you'd have one kind of here, and then here. And all I want is just one full period of it, but that, this green graph is the 2 cosecant minus 2x minus 1. And this is minus 3. This is up at 1. So basically to graph any of these secants and cosecants, you have to graph corresponding sines and cosines. So knowing these sines and cosines is a very important part too. Something you definitely want to know how to do going into the final.